Quantum field theory, QFT, is one of the most profound achievements of modern physics, providing the mathematical framework that describes how fundamental particles interact through underlying fields. It merges two of the most powerful ideas in science, quantum mechanics and special relativity, into a single theory capable of explaining the behavior of matter and energy at the smallest scales. At its core, QFT treats particles not as isolated points, but as excitations, or quanta, of underlying fields that permeate all of space. For example, the electromagnetic field gives rise to photons, while the electron field gives rise to electrons. Every particle we know is a manifestation of a corresponding quantum field, and interactions between particles are understood as exchanges of energy and momentum between these fields. One of the greatest triumphs of QFT is the Standard Model of particle physics, which describes the electromagnetic, weak, and strong nuclear forces in terms of quantum fields. This framework successfully predicted the existence of particles like the Higgs boson, discovered in 2012, and has withstood decades of experimental testing with extraordinary precision. Quantum electrodynamics, QED, a subset of QFT, explains how light and matter interact with an accuracy unmatched by any other theory in science. QFT also solved puzzles that neither classical physics nor early quantum mechanics could. By incorporating special relativity, it explains how particles can be created and destroyed, ensuring consistency with the idea that matter and energy are interchangeable, E equals mc squared. This makes QFT indispensable for high-energy physics, where particle collisions at accelerators like CERN routinely produce new particles. Despite its success, QFT remains incomplete. While it explains 3 of the 4 fundamental forces of nature, it does not yet incorporate gravity in a consistent way. Attempts to merge QFT with general relativity, such as string theory and loop quantum gravity, remain ongoing areas of research. Additionally, open questions about dark matter, dark energy, and the true nature of spacetime suggest that QFT is part of a larger, still undiscovered framework. Beyond fundamental physics, the influence of QFT extends into condensed matter physics, quantum computing, and cosmology. It has provided insights into phenomena like superconductivity, the early universe, and the quantum vacuum itself. Quantum field theory is not just a technical achievement. It represents a deep shift in how we understand reality. It tells us that the universe is woven from fields, with particles arising as fleeting ripples within them. By unifying quantum mechanics and relativity, QFT has given us a framework for probing the building blocks of existence, while leaving us with tantalizing mysteries about what lies beyond.